Hey everybody, this is Mike Bartles from the Hydrologic Engineering Center. This lecture is part 2 within a series of lectures devoted to parametric modeling from a hydrologic and hydraulic modeling perspective. Within this video, we'll talk about developing a representative dataset for use within a parametric modeling analysis. By the end of this lecture, you should be familiar with data requirements for a parametric analysis, and you should also know what IID stands for. You will also learn how to develop a dataset for use within a parametric analysis. Let's begin by revisiting the steps needed to perform a parametric modeling exercise or fit an analytical distribution. Within this lecture, we're going to focus on step 1, which is totally concerned with data. Developing an adequate dataset is foundational to any parametric analysis. You probably heard the common phrase, garbage in, garbage out. Well, that can't be more true than with parametric analyses. If the data is junk, your conclusions will be as well. When performing a parametric analysis, the data must be a representative sample of the parent population and can be comprised of homogeneous, independent, and identically distributed values. Throughout these lectures, I'll refer to the representative sample, which is what we typically have to analyze, as a child population. To be representative, the sample should be a random sample of possibilities from the parent population, which accounts for natural variability. The data should not include, or at least minimize, the effects of things like changing land use, including increasing or decreasing urbanization, regulation, for example, reduction in stages or flows due to upstream reservoirs or diversions, and large climatic variations or oscillations. There are other data considerations, but these are the big ones that we typically run into as modelers and engineers. The previously mentioned independent and identically distributed, or IID, data assumption is super important. Let's talk about the first part, which is independence. When assessing independence, ask yourself, is each peak unique and independent? Or are the magnitudes of one dependent upon another? In the image to the right, certainly the first peak is unique, but are the others truly independent? The third and fourth peaks aren't. What about the largest peak? Is that one independent? In the realm of hydrology and hydraulics, we typically look at the entire hydrograph shown here as a quote-unquote event and extract a single peak for the entire thing. And that would be the second peak in the image to the right. We typically extract maxima for the entire calendar year or water year in an effort to achieve independence because most watersheds settle back to a quote-unquote normal state within a year. But be careful with peaks that are close to your year demarcation. For instance, when using a water year which begins on October 1st and ends on September 30th, be very cautious to avoid using peaks at the end of September or beginning of October because you might not be able to assure that they're independent. Similarly, the child population must be an identically distributed sample of the parent population. And this means the sample should be randomly drawn from the parent population and not, or at least minimize, sampling bias. If climate varies over time, which it can sometimes do, and the sample is pulled from one time period that isn't representative of the entire range of climatic possibilities, then the data will likely not be identically distributed. A classic example of this phenomenon is exemplified in the image to the right, which is the annual maximum flow time series for the Red River of the North at Fargo, North Dakota. Climatic variations are evident in this sample. Visualize the average of the data. You can see that the average, or the mean, appears to be increasing over time. Also, look at the variability. Highs and lows. Look, they increase over time. How do you fit a model to this data set? That's a very difficult question to answer adequately. Using the exact same data set that I showed before, I computed a moving time window analysis and show the examples here. In this example, a window length of 30 years was used. After the statistics of the first 30-year time window were computed, the time window was moved forward by 5 years, and another 30-year time window was computed. And this process was repeated until the entire data set was analyzed. Notice how the mean, which is the blue line, standard deviation, which is the red line, and skew, which is the green line, changed pretty dramatically over time. Now, is the entire 1925 through 2019 time window homogeneous and identically distributed? Probably not. But a follow-up question for you to ponder is, how many violations of the IID assumption are you willing to live with when doing parametric modeling? It's not too hard to find a little violation in basically any analysis. In fact, many of the most commonly used parametric modeling approaches, for instance Bulletin 17C, they include some tools that are intended to minimize the negative consequences of this common violation. Some other considerations to keep in mind when analyzing data for a parametric analysis include the following. Are multimodal data present? Are you looking at an annual maximum series versus a partial duration series? Are there outliers present in your data? Is your data representative of intervals or point estimates? And do you need to transform your data? All the aforementioned topics will be discussed within this video. However, record extension is such a voluminous topic that this warrants its own lecture and video series. First up, we'll talk about multimodal data. An example of a multimodal data set is shown on the right as a probability density function. Notice the multiple peaks in this plot? They're all separate modes. Multimodal data is likely caused by a mixed population. Now, if this situation is encountered, you definitely should work on separating out the various causal mechanisms into their individual data sets. Mixed populations can be caused by, for example, a location being subjected to floods emanating from rain on snow events, summer thunderstorms, extratropical storms, or tropical storms. Now, it's unreasonable to expect that a single model could fit and accurately predict the probability distribution of floods due to all of these mechanisms. To best predict the exceedance probabilities of flood quantiles of interest, for example, what is the likelihood of exceeding some flow in any given year, it is best to split the dataset into the individual mechanisms, fit a model to each dataset, and combine the results into a single probability distribution using a mixed population analysis. We'll talk more about how to do that in a later lecture. Next, let's talk about annual maximum series versus partial duration series. An annual maximum series contains one and only one value per year. This is the most commonly utilized type of dataset when estimating flow frequency with, say, bulletin 17C procedures. Conversely, a partial duration series can contain more than one value per year. And this type of data is commonly used to estimate precipitation frequency. When plotted together on a normal probability axis, these two types of data for the same location and time window commonly merge somewhere between the 1 in 2 and 1 in 50 annual exceedance probability. Just to reiterate, the 95% use case when analyzing large or extreme floods will be to use an annual maximum series. Now let's talk about interval data. Up to this point, we've been discussing point data. However, there are situations in which interval data will be encountered and must be incorporated. In the figure to the right, the open black circles represent point data, where there is no uncertainty in the actual magnitude. The black bars in the red rectangle represent interval data, where there is uncertainty in the actual magnitude. The expected moments algorithm, or EMA, contained within bulletin 17C procedures can natively incorporate both of these data types. Also, other fitting methods like maximum likelihood estimation can as well. There's more on this to come. Sometimes data must be transformed to analyze relative changes instead of absolute changes. Other times, engineers and modelers are more interested in obtaining a symmetrical distribution about zero. Also, engineers may be interested in removing the effects of heteroscedasticity, which refers to the circumstance in which the variability of the variable is unequal across the range of values of a second variable that is used to predict it. So think of flow versus stage or something similar, where the variability of flow changes drastically as the stage increases in a typical in-size cross-section with a very wide floodplain. For a small change in stage, the corresponding change in flow could be small or extremely large, depending upon whether the flow is in or out of bank. In terms of common transforms, log base 10 is probably the most commonly used transform when dealing with flow. And this transformation allows for the user to analyze relative changes rather than absolute changes, and an example is shown to the right. Remember that the mean of the log transform values is not the same as the log of the mean of the values. However, this is by no means the only data transform that can be used, and I list out a few of the common ones at the bottom of the slide. In this video, we talked at length about data that goes into a parametric modeling analysis. The most important thing that I want you to take away from this lecture is that it's super important to investigate your sample to ensure it's comprised of independent and identically distributed values that are representative of the parent population. In the next lecture, we'll discuss how to select a model and parameterize it using your data. Thanks for watching, and I'll see you in the next one.